Yeah, so we can take the Pascal formula and iteratively plug it into itself. So let me write that down as a remark. Iteratively plugging Pascal's formula into itself we can write. So this is just we're basically gonna derive another identity here that's just a little more general than this one. So let me actually just do the derivation over here on this space that I have here. So we can start with n choose k, and we can write it as, n minus 1 choose k plus n minus 1 choose k minus 1. So just starting again with the regular Pascal formula. But then what I can do is take the term on the left, on the right-hand side on the left, I can just apply the same Pascal formula to that by basically replacing n with n minus 1 on the left side. So what is the formula for n minus 1 choose k? Well, it becomes n minus 2 choose k plus n minus 2 choose k minus 1. So I can go ahead and do that. N minus 2 choose k plus n minus 2 choose k minus 1, right? And then plus n minus 1 choose k minus 1. So I can kind of think of it that way. And then I can, well, I can do it again, right? I can take the n minus 2 choose k, and everywhere I see an n in the original formula, I can now replace it with n minus 2. And I'll get n minus 3 choose k plus n minus 3 choose k minus 1. So let's go ahead and write down at least one more iteration of this. So n minus 3 choose k plus n minus 3 choose k minus 1, and then plus n minus 2 choose k minus 1, and plus n minus 1 choose k minus 1. Okay, and we can kind of keep doing this for a while. Of course, I can't do it indefinitely because eventually this n minus k, the n minus 1 and then n minus 2 and n minus 3, eventually it will drop below k. And you can't have the number on top less than the number on the bottom. That's kind of what this is saying. So where do we end up at the end of doing this process a whole bunch of times is, I grabbed the wrong paper here. The final formula you'll have is you'll eventually get this down to k minus 1 choose k minus 1 plus k choose k minus 1 plus k plus 1 choose k minus 1. Notice that on the bottom we have always choosing n minus 1. Sorry, k minus 1. Let me say that again. So what's happening here is you're kind of noticing the terms on the right. Everything is always choosing k minus 1. So n minus 1 choose k minus 1, n minus 2 choose k minus 1, n minus 3 choose k minus 1. That keeps building and building and building. So eventually you can get down to k choose k minus 1, right? And then eventually this number on the top would be the same as the number on the bottom. And I realize it's k. And now, so where is that term? Technically, k minus 1 choose k minus 1 is the same as k choose k. So it's as if you could just as well replace it with k minus 1 choose k minus 1 so that the number on the bottom is the same on all of these terms. So this is just another identity which we have derived for n choose k. What we're saying here is you can just create a series of binomial coefficients where all of them are choosing k minus 1 on the bottom, and you're working your way down from n minus 1 until you hit k minus 1. You can't go any lower than that. And it's another formula for n choose k. So it actually will turn out to be kind of a useful formula. So that's why I wanted to write it down here as just an extension of the original Pascal formula. Okay, so that's all I wanted to do with that. It's mostly just a computational observation, but worth recording. Okay, any questions on that? Pretty straightforward. Okay, we're gonna kind of start something new here. The rest of today, I kind of want to talk about this binomial theorem. You may very well have seen this in a different class. It comes up even in calculus, strategies of proofs. you'll see it in analysis courses as well. It's not just a combinatorics idea, but it is certainly something we can talk about in this class. So what I'm going to do is sort of state the theorem that is the binomial theorem, and in the book it's theorem 5.2.1. And then we'll talk about it, we'll prove it, we'll look at the applications of it. It's definitely something that we want to discuss in this class. So what I'm going to do is I'm going to let n be a positive integer. So n is an element of z plus. That's just my notation for the positive integers. And then what we're going to say is that for all x and y, these can actually be any real numbers. It doesn't require that these be integers. But for all x and y in the real numbers, if we calculate the nth power of x plus y, so if we want to take x plus y and multiply it by itself n times, then there is a formula for this, which looks like the following. X to the power of n plus n choose 1 times x to the power of n minus 1 times y. And then the next term is going to be n choose 2 times x to the power of n minus 2 times y squared. And I'm going to keep adding terms like that, dot, dot, dot. We keep going with this. Eventually we'll hit n choose n minus 1 times x times y to the n minus 1. And then finally, the last term is just y to the n. So it's a fairly long expanded expression. Of course, mathematicians are going to prefer to write this using summation notation. So I will also give it to you that way here. We can think of this as a summation. This will be where k goes from 0 up to n. And what we have here is n choose k. By the way, remember n choose 0 is just 1. So you can imagine there's an n choose 0 on the first term, and n choose n is also equal to 1. So there's an n choose n on the last term as well. So every term has a binomial coefficient with it, and then some power of x and some power of y. And that's simply going to be x to the power of n minus k times y to the power of k. So this is the more formally precise way of writing the binomial theorem down using the mathematics symbols. Okay, so there's actually many ways to prove something like this. I'm going to give you, though, in the spirit of what chapter 5 is partially supposed to be about, I'm going to give you a kind of a combinatorial proof of it. Okay, makes sense after all, based on what this class is, that we should give a combinatorial proof. So the way I would think about this proof is that we can imagine taking x plus y quantity to the n and writing it out kind of longhand here, x plus y times x plus y times x plus y, and we go dot, 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 x plus y and x plus y. So there's going to be n factors of the quantity x plus y all the way across there. And you can think about foiling that out. You know, and how you foil something out is, well, you grab one of these, you grab one of these, you grab one of these, you grab either the x or the y each time. And you make one term. You make one term by grabbing exactly one of the terms of each factor. So you grab one of these, one of these, one of these, one of these, one of these. By the time you've done all that, you will have grabbed n things consisting of some x's and some y's, right? And that will make one term in your expansion. So let's just actually kind of spell this out in words here. So in this expansion, of the right-hand side, again, I'm going to be, for the next week or two, you're going to see a lot of these combinatorial proofs where I write RHS and LHS, right-hand side and left-hand side. In the expansion of that, we have a total of n x's and y's combined. So if I count all of the x's and the y's, there would be n x's and y's combined in each term. In each term. And so this just means that each term has some powers of x and powers of y, but the powers add up to n, right? So a typical term, just explain that part here, right? A typical term will have the form. Typical term will have the form, x raised to the power of, I'm going to imagine I have n minus k of the x's, and I also have k of the y's. Right, so this would be for some k. Or some k, which has to be between 0 and n inclusive. So k is an integer between 0 and n. We can write it that way. Okay. In constructing this term, the question would be, well, how many different times would I get exactly this term? Because I can get this term more than once. Maybe I grab the x's from the first n minus k of these factors, and then I grab the y's from the last k of those factors. Or maybe I start by grabbing the y's from the first k factors, and then start grabbing x's from the remaining n minus k factors. Or maybe I go back and forth. Some kind of a mishmash of choosing x's and y's along the way, as long as I choose this many x's and this many y's. Well, that sounds like choosing from n factors. I'm going to choose, let's say, k of those factors to grab the y from. Okay, so there are, I'm going to call this n choose k ways to choose k factors from which to take y. And then I'm just going to mention in parentheses here, the x's are taken from the other factors. The x's are taken from the other factors by default. So there's no additional choices with those x's. We're going to make the choices with the y's, and then by default, the x's have to be the other choices. Okay. And so if there's that many ways, n choose k, if there's n choose k ways of grabbing k of the y's, and by default, n minus k of the x's, then how many terms of this form do I have? Well, it's exactly n choose k. So there's n choose k times that this same factor occurs. So we're going to group them all together with a coefficient that kind of keeps track of all of them as a single term. So we get n choose k terms of the form. I know this kind of feels like a little essay. I know that is what it is. Combinatorial proofs do involve a lot of writing. N choose k terms of the form x to the n minus k, y to the k. And then finally, summing over all values of k completes our proof. It's almost like proof by cases, right? The cases are just how many y's do you take? Do you take 0 y's? Do you take 1 y? Do you take 2 y's? Do you take 3 y's? That's indexing this power of y to the k here, which has to be something between y to the 0 and y to the n. Make sense? Everybody feel like they could explain that? Of course, immediately what you can do is take this binomial theorem, and instead of just x and y here, you can sort of jazz this up a little bit to do something more complicated. So just let me show you a quick example before we actually go any further. Suppose I wanted to expand, just call this an example, I'm going to expand the quantity 3x minus 5y raised, let's say, to the 10th power. So we could imagine just like writing this out, right? Okay, so for the solution, all I would say here is, you know, by the binomial theorem, using the binomial theorem, right, to do this. I mean, that would be the natural thing to do. Anytime you're expanding a large integer power of some expression of this nature. So what you're going to have is that 3x minus 5y, quantity raised to the 10th. Well, that's going to be a summation where k goes from 0 to 10, right? The exponent, the n value here is 10. And we're going to have, what, 10 choose k. So the 10 is the value of n. And then the other thing to keep in mind here is that the x, what is the role of x now being played by over here? 3x, right? So you get 3x raised to the 10 minus k. And then you would get, what would be the y, taking the role of the y?
-5.
Negative, don't forget the negative, 5y, right? All raised to the k power. This is what it would be. If you wanted to, of course, you could write out a few terms. Maybe I will just for, I mean, this would be fine. Just leave it like that. But if you wanted to kind of see what some of the terms look like, when k is 0, right? When k is 0, you're just going to get the quantity of 3x to the 10th. And then when k is 1, you'll just get 10 choose 1, which is just 10 times the quantity 3x to the 9th times the quantity negative 5y, and then so on and so on and so on. The last one would be 10 choose 10, which also is 1, times the quantity negative 5 to the 10th. Okay, so that would be a very simple, just plugging in exercise that I think hopefully we can all handle. Nikolai?
So you can have it be. You can rewrite it to be n choose k times k to the n minus k times x k as well.
One more time.
You can rewrite it summation.
Uh-huh.
As n choose k times x, or I guess y with n minus k. To the k.
Yeah, certainly these two exponents are totally interchangeable.
When would you choose?
No, it doesn't really make a difference. I mean, on any given problem, you're going to, you know, have, if you have two terms there, you're just going to pick which one you want to put with the exponent of the n minus k and which one you want to put with the exponent of the k. It doesn't make a difference. The other point I should make is, well, if you had three things added here, what if it was x plus y plus z to the n? You could, of course, group together like the y plus z and treat it as a single entity and apply the binomial theorem to that. And then, right, so if, oh, let's write it down. I start waving my hands too much, right? So just as another little example, you don't have to limit yourself to just two expressions here. So what we could do is, you know, we could write x plus y plus z to the n by thinking of it as the summation as k goes from 0 to n of x to the n minus k times the quantity of y plus z raised to the k. So I can treat the y plus z, everywhere I see a y, I can just think of it as y plus z being raised to the k. Yeah.
Are you missing the n choose k for it?
I sure am. Let's try that again. N choose k, thank you, times x to the n minus k, and then the quantity y plus z to the k. Thank you. Absolutely right. And then I could also from there apply the binomial theorem within this expression on the y plus z part. So let's just see what that would look like. You're going to get a double summation, dare I say, right? So k is summing from 0 to n of n choose k, and then we'll have x to the n minus k, and then we'll have a summation, let's say L going from 0 to k of k choose L times y to the k minus L times z to the L. Okay, so I could do that. And then, usually mathematicians prefer to have all their summations sitting out in front. So we can move this inside summation out to the front and do it as a double sum. So k goes from 0 to n, and then L goes from 0 to k, right? N choose k times k choose L. Could write all that down, and then I would have just the powers of x, y, and z. So x to the n minus k, y to the k minus L, and z to the L. So you have to be a little bit proficient with summation notation here if you want to write a pretty clean answer down. But you can actually do that. Anybody want to do the 4-term version?
No.
No?
Okay.
We'll save that for the exam. I'm just kidding. Opposite. So that's a nice proof of the binomial theorem with just a couple of direct examples of plugging into it. I mean, we can also use the binomial theorem to prove things that are maybe slightly less obvious as applications of this theorem. So for example, what if I asked you to prove that the summation k going from 0 to n of n choose k times 2 to the k is equal to 3 to the n. So I could actually imagine, I think you're gonna have a couple of homework problems like this as well, where you actually have to plug numbers in. So now we don't see the x and the y anymore. The reason being that we're going to substitute values in for those, right? So for the solution to this, does anybody have a suggestion how we would do this problem? Take a look at your binomial theorem as compared with what we have here and see if you can line things up in a way that would
We're like missing in the sense like the x.
make this fall out. Pardon?
We're missing like the x component, right?
Yeah, we only have
The one.
one of the two. Only one thing is raised to a power here, and on the other side of the equation, we just have a number, which is 3. Kristen?
Or x.
Okay, we could do it that way, x equals 2, y equals 1, just to make it line up even a little bit better. I'm gonna choose x to be 1 and y to be 2, because the y variable is the one that's raised to the k power. Does everybody see this?
Yeah.
This is nothing that difficult. Plug x equals 1 and y equals 2, right, into this expression. So into the binomial theorem. And if you do that on both sides, right, obviously x plus y is 3. That's being raised to the n power. And then on the other side of the equation, you just have, the same n choose k.
Okay.
And then 1 is being raised to the n minus k, and 2 is being raised to the k. Seem okay? Yeah, nothing too crazy here. Just for curiosity, you could ask yourself what would happen if you plugged in, let's just do another quickie here. What would happen if we plugged in some different values for x and y? How about if we did plus and minus 1? Instead of 1 and 2, what if we did 1 and negative 1? So for x equals 1, because this gives us kind of something interesting, it's worth writing down. For x equals 1 and y equals negative 1, we obtain, it'd be a summation, k going from 0 to n, of n choose k. X is only equal to 1, so I don't need to write that term down. It's only the negative 1 power that matters, raised to the k. The y value is raised to the k power. And according to the binomial theorem, that should be equal to x plus y to the n. Well, what is x plus y? 0. So 0 to the n is just 0. And so if you actually kind of write out what this looks like, it's kind of interesting. You'll get on the left n choose 0 minus n choose 1 plus n choose 2. Powers of negative 1 just alternate, right? So you just get this alternating chain of remember when you add all these up, you get 2 to the n. Remember that from the homework, right? So you take the n choose 0 plus n choose 1 plus n choose, so you get 2 to the n. But when you alternate addition, subtraction, addition, subtraction, it comes out to 0. Okay. Another way of saying that is just that, I guess I'll write it up here at the top if you guys don't mind. I can move the subtracted terms to the other side of the equal sign, and what we have therefore is that if I take the binomial coefficients where I choose even numbers, n plus 0 plus n plus 2 plus n choose 4 and so on, that's equal to n choose 1 plus n choose 3 plus n choose 5. I mean, this isn't something that you would probably think of as obvious necessarily, right? So if you have n people and one person is tasked with putting them into groups of even size, and then someone else is tasked with taking those same n people and putting them into groups that have odd sizes, turns out that both people have the same number of ways of doing that task. It is bizarre. That's kind of a bizarre result. Or another way of saying it is, if you take any set of n objects, let's say, just think of your favorite number for n, like 100. N is 100. The number of subsets of 1 through 100 that have even size subsets is exactly the same as the number of subsets of 1 through 100 that have odd size. It's kind of bizarre how that worked out. But it is true. Okay. See, where am I at here? Great. Questions about the binomial theorem? At least for now, that's about all I wanted to say about it. Just want to make sure we were familiar with it. Nobody should go out with a math major, without knowing this theorem. Some of you have heard me say this before, but before COVID anyway, I always attended the graduation for the math department. And they actually had me as like the important person down in the front, like ushering people in and out. And I always was threatening that, just to make sure there was no like mistake with the graduation, that, I might have one last question before you walk across the stage and everybody cheers and so on, just to make sure there was no mistake. And I have to, when I think about like, what kind of question would it be? It would have to be some really important thing, right? This would be in the running, right? This is like a pretty big deal. Like, tell me the binomial theorem. We'll stop the music. We'll just hold the whole thing up. Everybody can wait, and we'll have you do the binomial theorem. And that would be, it's on that level. Right? It's right up there with the fundamental theorem of calculus. It's right up there with the fundamental theorem of algebra, fundamental theorem of number theory. So I know when I see you at the graduation, you're gonna be running the other direction. Oh, is that it? That's a good one. That's a good one. I gotta give it to you. All right. That was just a quick little chat about the binomial theorem. I'd like to go on to the next section and talk a little bit about combinatorial identities. This is still chapter 5. It's kind of in the same spirit of what we've been talking about here for the last day or so. These are just formulas that involve the binomial coefficients. Okay, so these are generally, when I talk about combinatorial identities, these are going to be formulas involving, n choose k. So the binomial theorem is a great example of one such formula, along with all of these applications of it. But there are, of course, a lot of others. And these are often proved, just make a little bullet point comment here. These are often proved by using a combinatorial argument. So I'll just underline that. We often like to prove combinatorial identities by using a combinatorial argument, and I mentioned this already last time what this is, which this is essentially, so I'll just explain it here. This involves, which involves counting something. This involves counting something in two different ways. It involves counting something in two different ways. And a lot of times, the hard part is figuring out what is the something that you want to count that's relevant for the identity that's in front of you to prove. So that's what we have to practice a little bit. Let me just add to this. So once we've counted something in two different ways, this will thereby, I'll just say thereby proving that the numbers in each count, you're basically going to do two counting arguments. And counting one way, you'll get one expression. Counting another way, you'll get a different expression. But since you're counting the same thing, whatever it is, whatever this something is, because you're counting that same thing, then the two counts have to be the same. So must, in each, proving the numbers in each count must have the same value. Yeah, that's the idea here. They must have the same value. I think the best way to get the hang of this is with some examples. And again, the hardest part is often figuring out what is the thing that you want to count, the something that you want to count that will facilitate exactly the expressions that are in the formula you're proving. So let's try an example of this. Let's suppose that I asked you to prove that k times n choose k is equal to n times n minus 1 choose k minus 1. This would be an example. Now, this one could just be done with the factorial definition of n choose k. I admit that, and that would be perfectly reasonable. But I would like to actually do this problem using a combinatorial argument, because there are going to be plenty of examples where we cannot get away with just a numerical algebraic manipulation. But this one already gives us a chance to kind of practice what I'm talking about here. So we give a combinatorial argument. I'm going to count something in two different ways. So can anybody think of a physical example of something where the number of ways that you could do that thing would be k times n choose k? Can you think of an example of something in the real world where you'd have, I don't know. Well, I don't want to start telling you yet. Probably thinking of n objects of some kind. Committees of size k. So I might have n people who are eligible for this committee, and we just want to make a committee of size k. Well, that would just be n choose k. But the left-hand side, of course, says k times n choose k. So it has to be more than just a committee of size k, but it's a great start, right? And the number of ways of making a committee of size k from n people would be n choose k. What could we sort of decorate that example with that would factor it up by a factor of k?
Maybe k choices to choose who's like officers.
Say again? I only want to make one committee. So I have n people, I'm going to choose k of them to be on the committee. And then among those k people, right, I now have k choices to choose a president of this committee, for example, right? Something like that. Does that make sense?
Yeah.
So let's suppose that the something that we want to count are committees of size K with a president. Okay, chosen from a group of N people. Okay, so that's not the only thing you could choose. That's not the only scenario you could create, but it's a good one. It's gonna work nicely. Yes.
Just thinking. Sorry, I have no consoles
Uh-huh.
and you don't buy any games, so you're like looking for what? It doesn't come with games, right? So that would be your looking multiplying. Okay. So it's like you have something and then you need to fill that one slot, but it's included in it. That makes sense.
Do you play video games?
I
Is
think-
that what you're talking about? Oh,
Well, it's like
I'm trying to understand. So you have consoles.
It's like going to the store, right, and you're buying a product and it's missing something, and you need to buy an extra, like, it doesn't come with a charger or your phone, right?
Uh-huh.
And so you would have to
So
get,
that's what this would be for.
you have to.
It's like, it's definitely, when I look at the left side, I definitely think of it as there's gotta be two subtasks. It's not just doing one thing. You have to do one thing and then another thing as well, right? So I'm gonna go back to the committee's example, but there are other examples that you could use as well. So let's count. Let me see how I wanna write this. Where did my notes go? It's this page, actually. Sorry. How did I wanna write this one? Consider. So here's how I'd like you to write this up. Consider the number of ways. Right, consider the number of ways to select a committee of K members. With a president. Or it could be anything. It doesn't have to be a president. It could be some officer position would be fine. From a group of N people. So you might have N people and you're talking about how many ways could you make a committee of K of them and select a president. So let me write down how many ways there are to do that. So method number one, write it. You'll see me do this a lot. I'll actually put the two ways of doing the count as two methods, right? So in this case, the first method is there are N choose K ways to select committee members. And then after you have those committee members, I do apologize, there's a fair bit of writing. You have to tell a story, right? Select committee members and then K ways to choose a president. Of the committee, and the president would be one of the K committee members, right? So then by the multiplication principle, I'm going to use MP for that. By the multiplication principle, there are just multiplying these, right? K times N choose K ways to do this. Now, I should point out that when I figured out that story, I was mostly looking at the left side of the equation so far. I haven't even looked at what's over on the right side. There's nothing that says you have to look only at the left side. If you prefer, you could actually have started by figuring out what you want to do based on what's on the right-hand side. Having started with the left side, we were able to make a story that fits the left side really well. The issue is, will it also fit the right side? So I'm hoping that it will make sense. And we just have to write down the explanation of it. And this, if it makes sense, it's going to be our second method. The second method. So can somebody explain how the right-hand side would actually also give us the number of committees of size K that have a president chosen? Instead of choosing the committee members first and then picking a president from the committee, what else could we do, Julie? Okay. And the rest of the committee would be one less person as well. Exactly. So this is, the right-hand side is basically just doing it in the other order. Choose the president first and then fill out the remaining committee members from there, right? But at the end of the day, you're still gonna get a committee of size K with a president. So you've counted the same thing in a different way. So there, let's just write that down. There are n ways to choose a president of the committee. And that president is one of the members of the committee. N ways to choose a president of the committee. And after you've done that, then there are only n minus 1 people left, exactly what Julie said. N minus 1 people left. I have to choose k minus 1 of them. There's that many ways to add additional committee members. And it's a lot of writing for the next week or so to get our wrists ready to go. But again, by the multiplication principle, there are n times n minus 1 choose k minus 1 ways to do this. Okay, we've counted the same thing in 2 different ways. Notice that I started off by telling you what I was going to count, and then I proceeded to explain how many choices I have for doing it in 2 different ways. And so those 2 ways have to be the same amount. Okay, so since, well, let's just say it this way. Equating method number 1 and number 2, we get the statement, which was k choose n minus k equals n times n minus 1 choose k minus 1. Exactly what we have there. So that's a good example of a combinatorial argument. This is a pretty easy one. I will tell you, they do get more interesting. I think over the weekend, you'll get a chance to practice this a little bit. We'll do some more. I want to do some slightly harder ones next week. So on Tuesday, come back, expect to see more of that. And we'll finish up chapter 5 and go on to the inclusion exclusion principle. That's going to be the next chapter. So thanks, guys, for a great day. I will see you all on Tuesday, if not office hours beforehand.